Hello class 12. In this video we are going to learn about semiconductors, which is a very important topic for you all from the examination point of view. And also semiconductors, these are materials, these are substances which has a huge role to play in our everyday life. All the computers, smartphones, your smartwatches, your calculators, everything, your television, electrical bulbs these days, LEDs, are all made up of semiconductors. So these are substances that has revolutionized the world. So how do we actually define semiconductors? Now, semiconductors are substances having electrical conductivity lying in between that of conductors and insulators. So substances whose ability to conduct electrical current lies between that of conductors and insulators are what are called semiconductors. Now, examples are silicon and germanium. These are substances which we naturally get, which are semiconductors. And there are some, alloys also which are made, like gallium arsenide, gallium phosphide also. Okay. Now, these are semiconductors, examples of semiconductors. Now, before we actually start discussing about semiconductors in a greater detail, let us first learn about something called energy band theory. Now, what is this energy band theory? Let us try to understand. In this energy band theory, we are going to learn about something called the valence band and the conduction band, something called the band gap or the forbidden gap, which is also called forbidden energy gap. So what are all these terms? Let us try to understand first of all. In order to understand valence band and conduction band, let us first of all try to visualize the atom. Let us take the atom of sodium, for example, in this case. Now, what happens is, we know this is the innermost orbit wherein we have 2 electrons. Then after, we have 8 electrons in the second orbit. And in case of sodium, the atomic number being 11, it has 11 number of electrons. So this is the outermost electron. Yes, this is the outermost electron, and the orbit in which the outermost electron rotates or revolves around the nucleus is what is called the valence orbit. And this, of course, the electron has its name. The outermost electron has the name valence electron. Now, in a material, we don't just get one atom of sodium. What we get is, we get a material of sodium. We get the substance itself, and in this substance we have millions and millions of atoms. Now I'm depicting atoms as circles in here. So there are millions and millions of atoms that make up this material, that make up this substance, sodium. So how we can visualize something called valence band is, so these millions of atoms are very close to each other, and thereby what happens is, every atom will have its own valence orbit. So these millions of atoms will have millions of valence orbit which are very close to each other. So this is how I interpret it. This is how I visualize it. So valence orbit, they overlap one on top of the other. Okay, these atoms being very close to each other. So we don't just, so to say, get one valence orbit. What we rather have is a series or valence orbit, different valence orbit overlapping one on top of the other, and thereby we don't just get one orbit. Rather, what we get is a band of valence orbits, which therefore is what is called the valence band. So it is a lot of valence orbits, so to say, overlapping one on top of the other, and thereby it's called the valence band. This is how you can visualize it. Okay, now what is this thing called conduction band? Now, again, talking about one single atom, this electron can simply jump out of its, being very far away from the nucleus, it can simply jump out of its valence orbit and roam about freely inside the material of the substance. And thereby this electron becomes free electron. The valence electron now becomes free electron when it jumps out of the valence orbit and is free to roam about inside the material of the substance. And it is free electrons which help in conduction of electricity. Please do not forget that. So only free electrons contributes to electrical conductivity. So to say, these free electrons helps in the conduction of electrical current or helps in the conduction of electricity means this area, this area in which the electron can freely roam about is what helps in conductivity, and thereby this area now in which the electron is free to move about has been depicted or is visualized as a band and is given a name conduction band, because in this region the free electron helps in the conduction of electricity. Okay, now this is what you will be asked in the exam to show. This is the conduction band, this is the valence band. In insulators, what happens is there is a huge gap between the valence band and the conduction band. So since there is a huge gap between the valence band and the conduction band, in the valence band you have lots of electrons in the valence orbit, so to say. In an overlap of valence orbits, you have lots of electrons, but it is difficult, so to say, since there is a huge gap between the valence band and the conduction band, it is difficult for the electrons to reach the conduction band. So to say, in case of insulators, there is lesser number of free electrons. In case of insulators, therefore, there are almost no electrons in the conduction band, because they have to overcome, only if these electrons in the valence band can overcome this huge band gap, which is of the order of 7 electron volts. Okay, so this is like the amount of energy the electrons need to reach the conduction band. So only if they have about this amount of energy, the electrons can reach the conduction band. Somehow they are supplied with this amount of energy, they can reach the conduction band. So this band gap, or something called forbidden gap or forbidden energy gap, is actually a value of energy. This is a value of energy that the electrons need or require to reach the conduction band. So in insulators, you have very less amount of free electrons. Semiconductors, in the valence band, of course, you have electrons. Okay, and in the conduction band also there are some electrons, because as you can see in the picture, there is a very small band gap between the valence band and the conduction band, very less compared to that of insulators. So in semiconductors, the band gap is about of the order of 1.1 electron volts or 0.72 electron volts in case of germanium. 1.1 electron volts is that in case of silicon. And as you can see in conductors, the valence band and conduction band, they are like overlapping. So to say, it's very, very easy for electrons to reach the conduction band. So there are enough electrons, large amount of electrons in the conduction band as well. So in case of conductors, there are lots of free electrons, so to say. So in conduction band, whatever electrons are there, those are free electrons, remember. In the valence band, whatever electrons are there, these are electrons which are revolving around the nucleus, remember. So, energy band theory is just a depiction of, how much free electrons are there in the conduction band, okay, or how much free electrons are there to help in the conduction of electricity. So in conductors, in case of conductors, there are lots of free electrons. In case of semiconductors, we have lesser amount of free electrons as compared to that of conductors, but more compared to that of insulators. In insulators, there are there are no electrons in the conduction band, and the gap between the valence band and the conduction band, these are called band gap, forbidden gap, or forbidden energy gap, which simply actually is a value of energy that the electrons in the valence band require to reach the conduction band. So in insulators, they need more amount of energy to reach the conduction band. In case of semiconductors, in between value of energy they need to reach the conduction band. And in case of conductors, a very less amount or no amount, there is no band gap, so to say. Okay, so this is about the energy band theory. In the exam, you will be asked to draw these pictures.